Hello, welcome back to Calculus 2. Today we have lecture number 7, which is on logarithmic differentiation. Today we're going to look at a new technique for finding derivatives. We have y equals f of x. In logarithmic differentiation, the natural log of y equals the natural log of f of x. And this approach will allow us to simplify functions algebraically in order to take derivatives more efficiently. Now let's recall the graph and the range of the natural log of x function. We know that as x approaches 0 from the right, the natural log of x is negative infinity. And as x approaches infinity, the limit of the natural log of x is positive infinity. If we transform those limits into graphical statements, we see what the graph of y equals natural log of x looks like. And we know that the natural log of 1 is 0. And because of that, the x-intercept is 1, 0. And the natural log function never crosses the y-axis. So this is going to be our approach in logarithmic differentiation. We take the natural log of both sides of an equation in order to do algebraic simplification. Remember, the natural log of xy is the natural log of x plus the natural log of y. The natural log of x over y is the natural log of x minus the natural log of y. And the natural log of x to the n is n natural log of x. These properties of the logarithm function will be very useful to us. We're going to do an example now, a very interesting function, y equals x to the x. Now, we see that the base is a variable and the power is a variable. So we can't use the rules for x to the n. We're just learning now how to differentiate a function where we have variables in both the base and the power. And that's going to be this technique of logarithmic differentiation. And here is our solution. The natural log of y equals the natural log of x to the x, which becomes x natural log of x. Now we differentiate. On the left-hand side we have 1 over y dy dx equals, and on the right-hand side we use the product rule. The first times the derivative of the second plus the second times the derivative of the first. We then multiply both sides by y, and we get the formula for dy dx. dy dx equals y times the quantity, 1 plus the natural log of x. Now here is another interesting example. We have y as a function. It's a rational function, and it's written as a product of linear functions raised to numerical powers. We would like to be able to use logarithmic differentiation to simplify this expression in order to find the derivative most efficiently and compactly. Now we take the natural log of both sides, and we use those wonderful properties of the logarithm function. So the natural log of y is 3 natural log of x plus 1 plus 2 natural log of x minus 7 plus 10 natural log of x plus 8 minus 6 natural log of x minus 5. And to differentiate, very straightforward, 1 over y dy dx equals 3 over x plus 1 plus 2 over x minus 7 plus 10 over x plus 8 minus 6 over x minus 5. And dy dx is found by just multiplying that equation on both sides by y, and that is the derivative. And it's arrived at in a way that's very efficient and uses less algebraic manipulation. So you can see here, we write it out clearly, that we can find dy dx using logarithmic differentiation, and it's always going to be f of x times the derivative with respect to x of the natural log of f of x. And so we can write it as just y times the derivative with respect to x of the natural log of f of x, or the natural log of y. And now, recalling the formula for the derivative of the natural log function and the basic definition of the natural log function, we have the general result that the integral of 1 over u du is the natural log of the absolute value of u plus a constant. We would like to use this formula for finding the integral of the tangent of u du. To arrive at this result, we write the tangent of u as sine u over cosine of u. Then you see that the derivative of cosine of u is minus the sine of u. And so we're able to use the formula for integration for logarithms, and we get that the integral of tangent u du is negative the natural log of cosine of u plus a constant. And we can just remove that negative sign by bringing it up as a power. Cosine of u to the negative 1 is secant of u. So we can write that the tangent of u du has the integral natural log secant of u plus a constant. And we can see another very important integral formula. The integral of the cotangent of u du is negative the natural log of the absolute value of the cosecant of u plus a constant. We just write cotangent of u as cosine u over sine u. And then, of course, we can integrate this since the derivative of the denominator is in the numerator. So we get the natural log of the sine of u plus a constant. And you can see we can write this as minus the natural log of cosecant of u plus a constant. You can use either form, whichever one is most convenient for you in the problem that you're working on. This concludes our lecture for today. Hope you can join us next time.